Hello, my name is Sushant Raikar. I'm a graduate student at University of Waterloo. Along with my teammate Spandan Chaudhary, have worked on this project as part of the CS 798 Network Softwareization course. This project is about stopping slow HTTP DDoS attack using SDN capabilities. Slow HTTP is a variant of DDoS attack which works in the application layer. Slow HTTP is one of the most powerful DDoS attacks and it's very hard to detect. A single machine can take down an entire web server. And it's hard to detect because there is no sudden influx of packets in the network. So traditional DDoS prevention mechanisms they fall short. In this project, we target two of the most popular slow HTTP attacks, Slow Loris and Rudy. SlowLoris works by forming HTTP GET connections with the web server but not sending complete HTTP header information. It sends part of header information at a time and forces the web server to keep its resources engaged with its connections. Thousands of such connections can bring down the web server. Rudy also works in a similar way. It forms post connections and sends post data very slowly, hence forcing the server to allocate resources. Now we'll discuss the methodology. The first step in stopping the attack is identifying whether the server is under attack or not. And the main concept we use is checking whether there is something abnormal going on. We do that by predicting the normal behavior and checking if it is different from the actual behavior. After lots of testing, we found that the best behavior to use for doing this is the average time the server takes to serve a request and memory utilization. We observe the average request time or memory utilization for a fixed time window and we predict the time or memory the next request will take. If we find that there is a significant difference between the predicted value and the actual value, we assume that the system is probably under attack. The prediction algorithm is explained in detail in the project report. If we deem that the system is under attack, we start looking for source IPs that tend to make lengthier connections. We monitor such IPs to check if they are frequently making such connection. And if they are indeed making such connections, we use HDN to insert blocking flow rules on the gateway switch. Now, let's take a look at our setup environment. We use the very popular Apache server, specifically version 2.4, for hosting the web server which will be attacked. We use Mininet to launch and perform simulations on the topology. We use ONOS as our HDN controller. And we use slow HTTP test, a neat script to perform slow loris or Rudy attack. We decided on this topology shown on the right mainly because of its simplicity and practicality. The main prediction logic resides as an controller application on ONOS. The only input it needs is the log data from the Apache server. We kept it this way in order to avoid any additional processing on an already busy web server. And often, production servers push the logs out of their systems into databases such as Elasticsearch. The end users of this web server are shown on the left side of the topology. It contains a mix of regular users, slow users, and attackers. The main challenge of this project is in identifying just those attackers and blocking them. Another crucial component is MOD underscore REQ timeout. It is a module that comes packaged in along with Apache Server. It does the work of setting hard timeouts on lengthy requests. We use this module for terminating lengthy attacker requests and producing logs which will help in their identification. Also note that having just this module without HTN support is not much effective in preventing slow HTTP DDoS. The reason for this will be shown later. We'll start with the demo now. First we'll SSH into the machine which holds the complete configuration. Then we are going to launch the mininet topology as it was described here. But before that we need to clear out any stale mininet data. Now we are going to launch the mininet topology. It is going to launch multiple hosts. H1 is going to host the Apache web server, and the other host will be serving end user clients along with attackers. So I'm going to enter H1 and see if Apache is working or not. It is working. Another thing I wanted to tell is this topology is pre-configured in order to provide constant load to H1. So if we check the number of connections, they'll be somewhere around 80 and constant over time. So now we are going to start a prevention mechanism, and there are two components to it. First is the log processor, which processes logs sent by the Apache server, and the second is the predictor. So I'm starting the log processor and the predictor. These are HDM applications which have begun, and now we can test whether it works or not with the attack. Let's try an attack from host 15. This script internally calls SlowHTTP test, and there are a couple of important parameters here. For example, this parameter tells that total 1000 connections will be made by this attack script, and this parameter tells the rate at which these connections will be made. So 16 connections will be made per second, and this is the attack endpoint. So this attack endpoint is on H1. So I'm going to start the attack. At some point the service is going to become unavailable, and that's when our prevention mechanism is going to kick in. Yes, as we can see here, the attack has been detected and the IP of host 15 has been blocked. We can try again with another attacker. This time 16. Before that, we can see if H15 is able to ping H1 or not. It shouldn't. And it's not. That's because of the blocking rule. We can try again with H16. We can try the different attack now, the slow loris attack. Service is unavailable and our attack has been detected and IP has been blocked. So this IP should no longer be able to ping H1. Yep. Yes, this is it. This is how our prevention mechanism works. Now, let's take a look at the results. The graph that's plotted here is for uptime, a very important metric when it comes to showing resilience against attacks. It shows for each second whether the server is up or not. The first graph on the left shows uptime when there is no defense. Please note that the server comes up after a long time in this graph. This is because the attack script was running only for that duration. It is possible that the attacker can leave the script running indefinitely, in which case the server will never car bomb. The second graph in the middle shows the situation where there are hard timeouts on request times. And as I told before, using just this approach is not enough. The reason being, if the attacker knows that his connections were terminated, he will start new connections. And the attacker will keep doing this. Therefore, we won't see any significant improvement in their uptime. The third graph on the right shows the results of our approach. Using predictor to detect an attack and using HDN to block the attackers yields a great improvement in uptime as compared to the first two graphs. In this graph, we see the total number of connections on the Apache server at any given time. The sudden rise in the number of connections occurs when the attackers start the attack. Similar to the uptime graph, there is no significant improvement in the first two approaches, but the useless connections are mitigated in our approach. These graphs are generated by the attack tool SlowHTTP test. It shows at any time how many requests are connected from the attacker's perspective, how many are yet to get connected, and how many are closed. We can see a significant difference in the green line, that is the connected line. We see in our approach, besides the initial bump in connected during the beginning of the graph, attacker connections never get connected to the server. That's it. Thank you for your attention. If you have any questions, please reach out to us at the given email IDs.